Hello, everyone. I will briefly overview the digital machining research I have been conducting at UBC since 1986. Well, I grew up in a small town called Bekirli in west of Turkey. Here you see my late mother and sister when I was in a primary school. Then I studied secondary school at the village. When I grew up and became 15 years old, my father thought I was a grown-up. So I ran a wine store on top of a mountain, which is called Pamukkale. And as you can see, my telephone number is 9, single digit. This was from 1969 to 1971. So I studied high school away from home, ran a wine store, and I had absolutely no holiday at all. I grew up in a winery. Those days, our winery was very poor. Now it is one of the largest winery in Turkey and run by my brother. And I studied my bachelor degree at Istanbul Technical University. I joined the university in 1971. I had plenty of hair, as you see. Those days we had no computer, no calculator. And those are my classmates. Unfortunately, I lost both of them. And I was a student in aerospace option. We were 14 students in the class. You can see all of us on aircraft tail. And I am still with the same girlfriend since high school, married with 2 children. I studied my master at the University of New Brunswick between 78 and 79, and studied my PhD at McMaster University in Canada. And I also worked 4 years in industry in between. And I joined the University of British Columbia in 1986 with $8,000 startup funding, 1964 vintage junk milling machine, which was not operational and abandoned in the corner of somewhere in the building. I took it apart with a summer undergraduate student, retrofitted that with the motion control card and PC. This became our first CNC machine, home built. We did this out of poverty because we had no money to buy one. Since then, our research in CNC became one of the biggest, I guess, in the world. Right from the beginning, I set up a vision to train good engineers with strong academic, fundamental academic training. Do research in manufacturing, which is relevant to industry, but make it all academic and publish all the findings in open journals. Machine tool is one of the most complex mechatronics system in industry. Kinematics, structural dynamics, control theory, sensors and instrumentation, tribology, CAD/CAM, everything, pretty much. And of course, we are cutting material, mechanics and dynamics of cutting subjects are also at the core. And our research in the laboratory covers entire machine tool engineering, starting from vibrations, design, control, monitoring sensors, precision machine and actuator design, multi-body dynamics of the machine tool, and so on. The laboratory grew up quite a bit in 37 years. We currently have 5 PhD, 7 masters, 2 postdoctors, 5 research engineers funded by industry. And we usually receive several interns visiting professors and engineers from different parts of the world. Up to recently, we were receiving about $1.2 million per year for research grants and contracts. The lab is fully equipped to conduct research in machine tool engineering. We publish over 210 journal papers and a book with 2 editions translated to languages. And the citation is pretty strong for our published work, as you can see here. And also, UBC opened a spin-off company which commercializes our research, and it is used by more than 300 companies worldwide. These are some of the machines we have in the laboratory. It's an old Hardage lathe, old Fadal CNC. We added 4th and 5th axis. It is completely controlled by our own CNC. And Quasar 5-axis machine tool with Heidelheim CNC, donated from Taiwan ITRI. And this is our newest machine, DMU 50 Machine Center. And we have CMM Micro-machine Center. And this is a 9-axis machine, which we built, designed and built and controlled in our own laboratory. And we built several actuators, such as fast tool servo, ultrasonic vibration assisted tool holder, and so on. I trained about 24 PhD students, and 13 of them are faculty members. They are listed here, and the rest are working in leading companies around the world. Also, the laboratory trained about 62 research masters and over 50 professional master students, and probably about 35 postdoctoral fellows. Our research is published in a textbook, first time in year 2000, and the second edition was published in year 2012. They are translated to Chinese and Turkish. I also wrote my memories in Turkish. The book talks about naive and stupid things I did when I was a child, young man. And also there are some stories from my town. The book does not talk about how good stuff I did in university and so on. That would be nonsense. It is just more fun to read. Unfortunately, it can't be published in English. It will lose its sense of humor. Now I can start talking about my research. Digital machining has been always my prime target. In a traditional manufacturing industry, you take the CAD model and experienced planners design the machine strategy and select tooling and cutting conditions. NC program is generated, put on the CNC machine, and hopefully the results are satisfactory. If they are not, you go back and repeat the trial and error cycle. My objective has been to simulate the entire machining operation like you would conduct a real experiment in computer environment. That's possible only if you model cutting mechanics, machine tool vibrations, kinematics, and dynamics of the machine tool. The physical system must be digitally modeled, basically. If we can achieve this, then we can optimize the operation and conduct the tests in digital environment as opposed to costly physical environment. That has been my objective. The first paper I wrote in this area was published in 1991 when I became CRP member. This was a paper from Dr. Spence's PhD thesis. We developed 2.5-axis CAM system, and we integrated physics of machining into the system and use that for monitoring and control of the process as well. Since then, of course, we progressed quite a bit, and we realized that this was a huge research task. Digital machining has three fundamental modules. The first one is CAD/CAM module. Second is modeling the mechanics and dynamics of machining operation. And we package our theories into one software called CUTPRO, which was released in year 2000, about 23 years ago. The third part is machine tool kinematics and CNC. Since we develop our own CNC, first out of poverty, later out of fun, we can also mimic the CNC. By integrating these three, we developed virtual machining system, and it was released to industry as a commercial product under the name of MACHPRO back in June 2011. I will walk you through now these three steps. The first one is CAM. Here, I show you a very simple prismatic part machined with a helical end mill. As the helical end mill moves along the tool path, it will engage with cavities and holes. So the geometry is not constant. It varies depending on the part features. When the tool goes over these cavities, the chip shape continuously changes as you see here. The chip shape is used as a boundary conditions to predict cutting force, torque, vibrations, and so on. Therefore, the cutter workpiece engagement along the tool path must be calculated. We conducted research in this area, but later Professor Steve Fang joined our department. This is his expertise. The second is mechanics of machining. We approach to this problem in two directions. One is so-called micro mechanics, where we consider temperature, strain, and strain rate dependent material properties in this plastic deformation zone, which is called cutting zone or primary deformation zone. And we use both finite element techniques as well as slip line techniques to predict stress, strain, and temperature distribution within this small cutting zone, which may be typically 200 micron by 200 micron. We also use macro mechanics approach to predict the forces in the cutting zone. Here, we have a typical oblique cutting mechanics model. By using material properties, tool geometry, and cutting conditions, we can predict the forces acting on the rake face, normal and friction force, basically. If we can predict these forces as a function of material property, then we can transform these forces to different kinematic configurations, such as turning, boring, milling, drilling, and the list can go on. But the common for all of them is the cutting process between the chip and the tool here. The rest is nothing but mathematical transformations. Therefore, we develop cutting mechanics models to predict the force between the rake face and the chip, and we adapted that mathematically to any machining operation. This was our philosophy and studied by Dr. Kluch, who is now professor in University of Manchester. Here is one sample result. The tool is taper helical ball end mill with variable pitch, machining titanium, which is very difficult material to cut. You can see the comparison between experimental measured cutting forces and simulated results, which are not bad. We use shear stress, shear angle, and friction coefficient of the material to predict these forces back in 1995, a while ago. When it comes to micro-machining, tool diameter could be as small as 100 or 200 micron. Chip thickness would be 2-3 micron only. The amplitude of the forces would be within 1 Newton as opposed to 1,000 Newton. Even the measurement of forces are difficult here, because if the rotational speed is too high, tooth passing frequency may be too high and resonate the dynamometer, and the force measurements will be incorrect. And we develop some compensation techniques to predict the correct force from measurements. One of the biggest problems in industry is machine tool vibrations. Here we have a diagram of a typical machine tool, which has heavy components such as bed and the column, medium-sized components such as headstock, and lighter components which move, such as spindle, tool holder, and tool assembly. Lower the spindle speed, you tend to use large cutters and vibrate large parts of the machine tool. If the tool diameter becomes smaller, you rotate the spindle at higher speed to reach certain cutting velocity. Then you tend to vibrate the parts with higher natural frequencies, such as lighter parts like spindle, tool holder, and the tool. Machine tools are flexible because they are made from steel. When the tool rotates and impacts the workpiece, these flexibilities are excited, and we create transient vibrations, which leave a wavy surface behind. When the second tooth comes and impacts, then if the vibrations do not diminish, we still generate wavy surface. Now we have oscillating chip. We have waves on the outer surface of the chip and inner surface of the chip. When the chip oscillates close to the natural frequency of the structure, the forces also oscillate exactly at the same frequency. Those high frequency forces start exciting the machine tool structure. And as a result, we have 3 types of chip. The first one, there's no vibration, which is impossible. All the machine tools vibrate. If the cut is very light, you hardly have any vibration naturally, but that's a conservative, non-productive machining. If the vibrations become unstable, we call that chatter vibration, where outer and inner waves on the chip surfaces have a phase shift. They shift relative to each other. These vibration amplitudes exponentially grow until tool jumps out of cut or you break something. The chip may be almost zero when the 2 waves touch. Then it can become large, almost 3-4 times larger than the feed rate. When the chip grows, the force grows, therefore the load on the tool and the structure grows, which may cause tool breakage or damage to the machine and the part. The objective of scientists is how can we make these 2 waves as parallel as possible, which is physically impossible, but you can get close to this situation. Imagine a case when these 2 waves are parallel. Then the machine is allowed to vibrate, but the chip thickness remains constant, like here. Therefore, cutting force also remains constant. Cutting force doesn't grow. In this case, we are in highly so-called stable zone in cutting. If we take a look at a typical mathematical model of the chip, first one is the static chip thickness. In milling, its sinusoidal varies as a function of tool's rotation angle, phi. This is due to rigid body motion of the machine. Then we generate vibrations at present time t. The vibrations in x and y directions are superimposed in the direction of the tooth, phi. And also, we consider vibration marks left during previous tooth period. So the time delay Tj here is the delay time between present and the previous tooth. Again, we project the vibrations. When you sum these three components, you get the true chip thickness, which is a long equation. Since the tool is rotating, phi is changing. Therefore, the chip thickness is changing. Since vibrations x and y are also time varying, they also change as a function of time. As a result, we have time varying chip thickness, but it is periodic at tooth passing frequency, which is inverse of capital T here. When the tool is in the air, then we have no chip. So we have discontinuity, which is governed by G function here. This is just to give a window of theory in stability. If we take the most simple case, 2 degrees of freedom, that means single degree of freedom in X, another single degree in Y, and we have periodic time varying coefficients A here, matrix, and we have vibrations with a delay terms here. Since this is non-diagonal matrix, this is periodic coupled delay differential equation, which is difficult to solve. And Dr. Budak, he's now professor at Sabancı University, solved the stability in his PhD thesis in our laboratory back in 1994. And we proposed 2 solutions. One of them is zero-order solution, which I presented in CRP, and the other is multiplicative solution that we published in ASME. Zero-order solution is very straightforward. KT, KR are the material properties. FRF is the dynamics of the machine. And we reduce the problem, stability problem, into an eigenvalue problem like this. Second-order quadratic equation. A0 and A1 are material and dynamics dependent coefficients. Omega is the eigenvalue with real and imaginary parts. Physically, the eigenvalue is equal to depth of cut, material's cutting force coefficient, and the delay term, which contains spindle speed. So if we solve the eigenvalue with real and imaginary parts, 2 knowns, we have 2 unknowns, depth of cut A and the speed. We can solve the stability diagram. This was our contribution to the literature, which is now widely used worldwide. For example, this is a cutter with circular inserts, and blue one is numerical time marching solution, which took about 24 hours. Red one is analytical frequency domain solution, which took less than a second. In industry, no one will wait for 24 hours to look at the possible solution for a chatter. But people can wait for a second, and the results match almost perfectly, as you see, which proves the accuracy of the theory. We launched this theory to industry by developing a software called CUTPRO. The user gives impact blows to the cutter with instrumented hammer and measures the vibrations. We measure the quick response function. We automatically fit curves to identify model parameters such as natural frequency, damping ratio, and stiffness. We use work material and tool geometry coupled with the dynamics of the machine, which is measured, to predict stability charts. This is the stability chart, means how deep you can cut at which speed. You have to operate the machine under the stability curve. For example, here, the most productive cutting conditions seems to be 7,500 revolutions per minute, about 6 millimeter depth of cut. So this is used by NC programmer to generate part program. And here is an example at 15,400, the machine chatter. This way, you can improve the productivity of the machine tool drastically. We work on other issues as well. Here is the animation of chatter development. I borrowed this from former student, Dr. Mehdi Aynian, and it's a very good illustration to show how instability occurs in machining. This is from one PhD thesis. Mexican company approached to us because they had pipe failure at the threaded joints. In the subsea application, this could be environmentally disastrous. If during threading, this pipe is highly flexible, it has so many mold shapes, and if it shatters, the wall thickness of the threads would not be uniform. In some locations, it would be so tiny, and it would be sheared during fatigue failure of the pipe. And the project was to model this complex process, and we did. And we packaged the mathematical model into the software and released it to the company, and also published everything in open literature. Another example is blade machining. This is an impeller or compressor of an aircraft jet engine. They are usually machined from titanium and nickel alloys, very difficult materials to cut. They are machined on 5-axis machine centers. Since blades are so flexible plates, it is easy to excite them and cause loss of chatter vibrations, as you see here. Then it's like unacceptable. The project was to digitally model the entire blade machining operation in digital environment. Let's say this is the blade. At each point, flexibility of the blade is different. Furthermore, as we remove metal along the tool path, we are changing the mass of the structure continuously. Therefore, blade dynamics is also changing as a function of time. If you freeze the process, run finite element at each 1-2 millimeter steps, it would take days to simulate the operation. Therefore, Dr. Thesis studied subtraction techniques to update FRF of the blade without going through eigenvalue solution for the full finite element model. The steps are as follows. We can predict the forces. If we know the cutter workpiece engagement, this is known. Then we predict FRF along the tool path as the mass is removed. We include contact between the flank face of the tool and wavy surface, which is called process tapping, to predict stability charts. Then, along the tool path, we can tell the engineer, look, you don't have any chatter in this region, but here the blade is too flexible and you are machining aggressively and you will get chatter, which will be unacceptable in production. So the engineer can improve the tool path until the chatter is gone. We can also predict the deflection errors left on the blade. For example, here we predict about 80 micron deflection here, and measurement is also close. We are still studying this. It's a highly complex problem. We can never probably perfectly predict the outcome, but as you see, we are not that far away from measurements. Now we have another student, Behnam, who is about to finish his PhD on the same topic. And hopefully we will release this to industry within a year. All of these physics-based models are incorporated into digital simulation software called MACHPRO, and the mathematical models were developed by Dr. Murdo in his PhD. We include chip thickness, force, torque on the spindle and power, drive motors, axis limits, all of them as constraints. We give the NC part program to our software called MACHPRO. Not only we simulate the process, like you conduct a cutting test on the machine, put sensors and measure the states, you can predict ahead of the time, everything. And also we optimize the NC program to adjust it to fit to the machine without any tool breakage, excessive deflection, overloading the spindle, and so on. And these are some results from our partner, Scientific Karamat, back in the year 2010. This is aircraft rib. This is turbine blade. On the left-hand side is the original NC program. On the right-hand side, you see modified NC program. We don't modify the tool path. We just optimize speed and speed. And you can see the productivity gain is not bad. And this is conducted in year 2002 when we received the first Morisaki machine. The wall thickness of this part is only 150 micron. The height is 35 millimeter. The material is aluminum. The objective was to cut a highly flexible part without any vibration during the first trial, and we did. Here is another sample result from our industry partner, Kerala. This was not done by us. This was done by my former students who work for them. On the left-hand side, before applying the know-how. On the right-hand side, with the application of digital machine know-how. And this is the only thing which I'm allowed to show. And you can see cycle time prediction for this case is 62%, and the surface finish is so visible. This comes directly from the machine center. We also work on flexible multi-body dynamics of the machine tool towards machine tool design. When the machine tool parts change their location during machining, their dynamics also change. We call this pose or position-dependent dynamics of machine tool structures. We develop some substructuring techniques to calculate the dynamic behavior of the machine fast in a computationally efficient way. Also, we have parallel approach, experimental approach. This is our machine. We model the machine using model analysis tests. And these are the substructures of the machine, which are connected to each other with springs and dampers, which are not known. We identify these springs and dampers from experimental model analysis, and we develop virtual model of the machine tool like this. Here on the left-hand side, we have digital twin, which includes machine tool dynamics, servo controller, CNC, and cutting process. On the right-hand side is the real machine. This way, you can realistically simulate the behavior of the machine along the tool path. Another project is spindle dynamics. And back in year 2000, Boeing approached us and they complained that they cannot use high-speed spindles at the speeds they want. So we had a joint project together with Boeing, Siemens Weiss Spindle Company from Germany, and our lab. Weiss developed a spindle for us, instrumented with lots of displacement sensors. We put the spindle on our machine. And we digitally modeled the spindle dynamics by developing finite element model of the spindle ourselves. The most complex part was nonlinear bearing stiffness model, which changes as a function of preload and speed. Here we gave an impulse load on the real machine, real spindle, and measured the vibration. And we applied the same impulse load on the digital model of the machine. You can see the responses are almost the same. And here you can see the fixed pulse function measured at the spindle nose and also predicted from digital model of the spindle. They match. Only model damping ratios are borrowed from existing spindles. We also conducted cutting tests, measured the cutting force, and the spindle chattered. As you see, the forces are growing exponentially. We applied this measured force on the digital model of the spindle and predicted vibrations along the spindle shaft. You can see sample measurements compared against simulations here, about 3-4 micron. So we can predict the performance of the spindle. What is the practical use of this? Now the engineer can design the spindle on the computer and conduct cutting tests on the screen as well, realistic cutting tests, without manufacturing the prototype of the spindle. This way, not only you can accelerate the design of the spindle, but testing of it as well. So there is a strong saving from time, money, equipment as well. Now, the current research includes integration of bearing faults, such as chipping on the inner outer rings of the bearings, damage on the ball itself, and wear on the taper of the tool holder, and so on. We incorporate the mathematical models of these faults to dynamic model of the spindle. And we use the digital spindle to simulate the dynamic behavior when the spindle has faults. Then we use this digital model, which is experimentally proven, to train artificial intelligence neural networks and apply machine learning theory to diagnose the failures on the spindle, faults on the spindle. Most of it is trained using simulation data, which is free. Then we use only few experimental data, as you see here, to fine-tune the neural network parameters. And you can see the results are almost 99.8% here. Our laboratory also conducts research in mechatronics and precision engineering. These are some actuators we built. And this is titanium casing with piezo stack in the center. And we created flexible springs here. So when we apply, let's say, 1000 volt to the piezo stack, it expands by about 40 micron, and it pushes the tool forward by controlling and regulating the voltage and measuring the displacement of the tool. We can control position of the tool tip within about 30-40 nanometer. Here is the step response. The input is 5 micron, as you can see. The output is also 5 micron precisely. And we developed sliding mode controller to compensate hysteresis of the piezo and disturbance of the cutting force. This was magnetic actuator for active damping of very large boring bar. This is another example. This is magnetically levitated rotary table. And magnetic levitation principle was invented by my colleague, Dr. Shabangu, and we co-supervised this project together. Now it has one company, and this company is growing quite rapidly and very successful. This was a master thesis of mine. This is the base, which is equipped with capacitor, and we have magnets between the stator and the rotor. The table lifts off maximum about 200 micron. It can rotate flex, as you see, but it can also move Y and Z direction and rotate around the mark. Develop this design, fabricated, including fabric and controller. Everything was done in the master. By the way, the sound that you heard is not coming from external speaker. The frequency, the bandwidth of this system is so high. Mark played Beethoven in his iPhone, but connected earphone outlet to the amplifier of the table. So this mechanical table is acting like a speaker. It's so fast. Then we put this 6 degrees of freedom table on a 3-axis micro-machine center, which we built ourselves. So it became a 9-axis machine, completely controlled by our own CNC. This research was conducted by Alexander Yuan, who was working as the chief conferential of Hyperloop. Now he switched to another company as a control manager. This is a highly sophisticated machine. It's a 9-axis machine with 4 redundant kinematics, so it has a very complex kinematics. And trajectory generation is also complex because we have to profile the motion for all 9 drives without violating jerk and acceleration and velocity limits of any joint. Then the machine has geometric errors, which have to be measured with laser and ball bar, modeled and compensated in real time using a controller. Since we have dual actuator in some directions like X, Y, Z, we have to have dual controller. So all of them are studied in one PhD thesis. For example, this is the dual actuator. As you see, it's much more precise because one actuator has only about 20 25 nanometer precision, the other has 2-3 micron precision. By using the two, we can lock into the target. And the machine really cuts. Another microelectronics device is 3 degrees of freedom ultrasonic vibration tool holder. This is the tool holder. You can see springs here, lips, which are tuned in such a way that the tool holder has a natural frequency of about 17 kilohertz. And these are the piezo stacks oriented in 3 different directions, so they can create force in 3 directions. And if we excite the actuator at its natural frequency, we have resonance and amplify the vibrations. Also, we develop a controller by measuring only current supplied to the piezo actuators. We can predict exactly where the tooltip is and what the tool velocity is. This is the controller. And you can see this is the result. We can have a circle with 8 micron radius or ellipse because we can control the position in real time. And we also cut a workpiece with this tool holder. As you can see, the cutting forces are reduced by about 30%. Such tool holders are used mainly for machining composite materials to break fibers at very high frequency. This is another master thesis project. This is adaptable tune boring bar. This is a long boring bar, and this is the cartridge, which has tungsten carbide mass supported by O-rings at the 2 ends. There is oil inside. This research was done jointly by Sandvik Kramat engineers in Norway. Silent tool company engineers, basically. They have this technology. What Derry Lappin did, he developed magnetic actuator. Without any contact, he was able to apply impulse force on the boring bar. We measured the vibrations using non-contact probe, and he put servo motor on a ball screw attachment, which is at the end of the boring bar here. So computer automatically tunes the spring constant, which is O-ring here, by compressing or releasing it. This way, we can increase the dynamic stiffness of the boring bar. This is another example of this is just a little of real machine vibrations. These days, we are working on digital twin. What is digital twin? This is the real machine. This is the virtual machine. And we simulate the real machine, but we also measure the states of the real machine during machining, and we exchange data between the two. And this is our kind of big idea. On the right-hand side, we have the real machine with sensors. On the left-hand side, we have digital twin model, which are already commercialized. So we collect data from the machine tool and automatically calibrate some of the uncertainties in the digital model, or we can send information to the real machine tool before things happen in a feed-forward fashion. We also collect data from machine tool for long-term machine tool health monitoring, such as spindle bearing condition, feed drag condition, and so on. One example here is prediction of cutting force without using a sensor. We measure the current from the CNC, and we correlate that current to the cutting force acting on the workpiece. To do this, you have to model the friction, ball screw dynamics, dynamics of the electrical winding of the motor, amplifier, and so on. For example, when you measure the transfer function between the applied force on the table and current on the motor, these resonances are due to ball screw dynamics. So if you operate the spindle at this frequency, you are not getting correct force measurements anymore because they are distorted. We develop Kalman filter to compensate these. Now the red dotted line is equal to unity up to about 200 hertz. That means we compensated the disturbance of dynamics. The proof is below. Blue one is predicted force from current, which is wrong. Black one is the reference force measured with dynamometer. Red one is compensated version of the blue with Kalman filter compensation. Now it's correct. And this is used in monitoring integral bladed rotor machining, as you see. Here is the measured and predicted cutting forces. Measurement is done with rotating dynamometer, which is laboratory equipment only. The other can be used in production. That means no sensor. We measure the current from the CNC and predict the force.